Hi, my name is Taylor Burke, and this is my video over reaction mechanisms for Chem 122. So to start off, the easiest way for me to understand a mechanism is to look at an overall reaction. So here is an overall reaction right here. Now, if I think of it, the reactants to me are like the ingredients to make a cake, and then the products are like the cake. So technically this is true. All of these turn into this. All these ingredients turn into a cake. However, if you've ever made a cake before, you know that's not how that works. There's steps. You cream the butter and sugar, you add the wet to the dry. That's how I think of mechanisms. So here is a 3-step mechanism, and what I want you to notice is right here when it's saying fast, slow, and fast, this is talking about the rate speeds of each individual step. Now, your slowest, and these will be given to you. The slowest step is your RDS, or your rate determining step. Think of it as you can only be as strong as your weakest link. You can only be as fast as your slowest step. So from the slowest step, you'll also derive your rate law. There's also a few other parts to a mechanism to be able to find. One of them is intermediates. So I've underlined them in purple, but that N2O2 and that N2O2, since they're on either side of the equation, how I like to think, if it's on the left and then on the right, you can cancel them out. Same with the N2O and the N2O, so you can cancel those out. Intermediates are created in one step and then used in another step. So they're not in the initial reactant and they're not in the final product. To start off, I'm going to look at a simpler mechanism where the RDS, or the slow step, is the first step. Now, from a mechanism, you can derive a rate law and you can find the overall equation. You can also prove that your mechanism is valid by comparing it against a given rate law and overall equation, or overall reaction, I'm sorry. So on this mechanism here, the purple, I have the intermediates, the red, NO3 and NO3, NO2 and NO2, those are our intermediates, so they get crossed out. I always find the overall reaction first because then you find your intermediates and it helps out for later on when you're doing your rate law. So right here in red, I have the overall reaction wrote out. So what I think is you just drop it down. So anything that doesn't have red underneath it gets dropped down. NO2, and then we have CO. And then over on this side, we have NO and CO2. So this is our overall equation. So those, easy enough. And that's the same way it works on a 3-step as well. You just cancel out the intermediates and you drop it all down. And if there's multiple of something, you can write a 2 coefficient in front of it. For your rate law, this is the different portion. Your rate law, like we said, comes from the rate determining step. So this is your slow steps. This is your rate determining step. And we know that rate law is rate equals K times the concentration of the reactants raised to the order. So these are reactants. So our rate would be rate equals K times the concentration of NO2. Since there's 2 NOs, it's raised to the second power. Simple enough. For a mechanism where the first step is not the slow step, it's a little bit trickier. You go through and you cancel everything out and your rate law is still from the slow step. So you'd think it's H2 plus N2O2. Like this would be what you're using. So it would be rate equals K times the concentration of these two. However, if you see that purple line, this is an intermediate. That does not work. You cannot have an intermediate in your rate law. So you have to remove it. So you use, if you see right here, there's an equilibrium sign. This means there's a forward and a reverse reaction. So you use these and you set the rate laws of the forward and reverse reaction equal to each other. Then you divide it out so that your concentration you're wanting, the concentration of your intermediate, is by itself. This one's simple. You just divide by K. I wrote -1, so I know it was the reverse reaction of the first step. And then you get this right here. But then you have to plug it into your rate law you've created from your mechanism. And you get this, but that looks really messy. There's a lot of K's going on. However, K is K. It is the rate constant. So it can simplify to rate equals K times H2, the concentration of H2 times the concentration of NO raised to the second power. And this matches our experimental rate law right here. So we know we did it right. Before I go into the practice question from the exam, just want to briefly show one of these. So this is an energy diagram for a 2-step mechanism. this is the energy on the y-axis, the progression of the time on the x-axis. This red line is showing the energy it takes for the reaction to occur. These hills are steps. The taller the hill, the more activation energy. The more activation energy, the longer it takes. And the one that takes the longest is the slowest. So this is our rate determining step. So we also have our positive delta H1 right here. This is because on our first step, we started down here and we ended up here. So the difference between these energies is a positive difference. So we have a positive delta H. It means it took energy to happen. Then you go to the second step, and my lines are a little swirly to make, but you can see it go back up, and we have more activation energy being used, but it's smaller. So we have our delta H of the second, delta H of the second step, and it's negative because it ended lower than it started. And then if you look overall from the starting energy, so that's that line right here, to our ending energy, this line to that line, you can see that our end is below our starting. So that means there's a negative delta H overall for this reaction. Now to discuss the question, I went with question 12. So it says a proposed mechanism for a reaction is, and it has 3 steps, and it says fast, slow, and fast. And it's asking us to find the rate law expected for the mechanism and the overall balanced equation. Again, look, we have the equilibrium sign, and your RDS, or your rate determining step, comes from your slowest. So this is a second step mechanism. So then you're going to go through. I write RDS so I know where it's at so I don't lose my place, and I cancel out the intermediates. And then what I always do first is, like I said, I write the equation out. So then I know this. It's hard to read backwards, but C4H9Br plus 2H2O turns into C4H9OH plus H3O plus Br negative. And like I said, you just swipe off those intermediates and then you pull down. Since there's 2 H2Os, it'd be 2H2O. But yes. And then for our expected rate law, it comes from the rate determining step. So you'd think it would be C4H9H2O. Wrong, because of the intermediate rule. It'd be a lot easier without it, but there was a reason for it. And so because of that, we do what we learned the first time. We see this equilibrium sign, and we set this side and this side, because you can see here is that intermediate, and we pull it by itself. It's a little tricky to do that, especially on this equation. I will admit it threw me because I wasn't planning on having it not simplify all the way. But we set our positive or forward reaction or negative reaction, and then to simplify that, to get this intermediate by itself, which here I can highlight the intermediate so you can see it a little better. That C4H9 is our intermediate that we're wanting to get by itself. So we do some algebra, and we take the K -1, I put -1 so I know it's the reverse of the first reaction. I divide that off, and I divide Br to the negative Br minus off of it. Well, it looks like this. I took off the Br for some reason in the test. I think I just didn't expect it to look that way, so I thought I must have done something wrong, and I just took it off, which is not what you're supposed to do. But this equals our intermediate. So then we put this into the equation where this intermediate originally was. And again, we see we have a K, another K, and another K. K is K, it's a constant. So now we have this, rate equals K, and then the concentration of C4H9Br over the concentration of Br times the concentration of H2O. So that is our rate law. But yeah, overall, I really like reaction mechanisms. I think they're very interesting. I think there's some things you can get stuck in, and I definitely got stuck during that question, but I really like them because you can kind of check your answer. Also, I've talked about it all. All right, thank you.